Well, the U doesn't have a C to give. So I have to write it like this. Any objections?
1. This is just 1.
That is just 1. No one objects to that?
Yeah, great.
What about that?
Yeah. Also fine.
This is starting to look like an eye test. Yay?
Oh yeah.
Now, this is very, very, very useful for us. So, I don't know where I am in my notes anymore, but so this is an invariant. So E squared minus PC squared is something that that we can count on. I'm going to show you a mnemonic device. Do you guys know what a mnemonic device is?
No.
A mnemonic device is something that's meant to help you remember stuff. That's why we gave it a name like mnemonic device, because everyone's going to remember that, right? So the mnemonic device that has stuck with me, it's stuff like which way do you, like if you're screwing in a screw, what direction do you turn?
Right?
So lefty loosey, righty tighty is the way that I remembered that one. Yeah. Let's see. If we were looking at, I don't know, there's lots of mnemonic devices. There's one for the categories of stars in terms of surface temperature. Astronomers frequently give killer midterms. The A, F, G, K, M. I'm missing some in there. Clearly that mnemonic device didn't stick. The 4 Galilean moons of Jupiter, Io, Europa, Ganymede, and Callisto. The one that was given to me for that is I eat green carrots.
Oh, you eat green carrots.
I've never been able to forget that. So oh bother, astronomers frequently give killer midterms. So from warmest to coldest. The sun is a G-type star. Oh bother, astronomers frequently give killer midterms. The mnemonic device I'm going to give you for this, right? Do I actually eat green carrots?
No.
I do not. Look at me. Do I look like I eat vegetables? Carrots are vegetables, right?
Looks like you eat a lot of vegetables.
So Oh bother, do astronomers frequently give killer midterms? I don't know. But, so I'm not telling you that there is anything in this other than helping you remember. I don't think that there is any magic in what I am drawing for you. So don't, well, I mean, always search for deeper meaning, but I don't think that there is actually any deeper meaning in this. But if you have a right triangle, right, a squared plus b squared is equal to c squared,
Yeah.
right? So e squared is equal to er squared plus pc squared. Or I could call this, so.
What's PC mean? Oh.
It's
P-
momentum times the speed of light.
Okay. Because I computer PC.
Yay?
Yeah.
So this is just to help you remember this formula. If you're ever stuck on a deserted island, this equation will save your life if you need relativistic momentum for something.
Okay, good.
So, but I don't think that there is actually any deeper meaning in.
We have already learned so deep, so far.
So, let's see. Do I have, and I even have a little bit of time here. Okay, so, questions, comments, concerns about any of this stuff?
So what's gamma U again?
It is kind of a measure of how relativistically funky your system is.
Oh, okay.
So this object moving relative to you, the faster it moves, the more you need to take relativity into consideration.
Oh, okay.
Do we, like, if I'm moving at 10 miles an hour, and,
Too slow.
well, that's not my question. Like, if I'm moving at 0.5 c,
Yes.
and another thing is moving 0.75 c,
Relative to you, or relative to the person who says you're moving at 0.5 c?
relative to the person that says I'm moving at 0.5 c,
Sure.
would the gamma there, would I have to plug into the Lorentz?
Yeah, so you would need to, so if what I'm hearing you say is, here is ancient Mark. Anyone ever read Le Petit Prince, The Little Prince? Really? Oh, you should. Little boy has his own little planet. But let's say that I'm sitting on my own little world, no germs whatsoever. We're so happy. And Chris just told me he's moving at 0.5 c, according to me. And then Dimitri is traveling 0.75 c.
Can it be in the other direction?
Sure. Dimitri's ship is so cool it can fly backwards. So,
So the U in gamma is the speed relative to the
So you would need to find what you say Dimitri's speed is. And that's the Lorentz velocity transforms, right? To get how fast you say he's going, that value is what you would plug in here. Yay?
Yeah.
Do y'all get what Chris is asking?
No.
Okay.
Did you ask?
So as always, I get to be the unprimed frame.
Okay.
So this is you, Chris, and this is you, Dimitri. Who measured those?
You.
I did, right? Because I get to be the unprimed frame. If Chris wanted to make a momentum determination for Dimitri, the first thing he has to do is he has to solve our for UD prime. Yay? This is also going to equal what? Between the single prime and double prime frames. It's also equal to V, right? So we have this single prime frame, we have my frame, which ceases to mean anything once he knows what UD prime is. And then we've got S double prime, right? The speed, what is the speed of the S frame according to Chris?
Negative 0.5c.
Minus 0.5c. So what is the speed of this frame? Oops. What is the speed of this frame according to Chris?
1.25C?
Well, I have to
Negative.
plug into the Lorentz velocity thing to find out. But
So-
that's really weird to me, because I don't understand, like, so, if we have a car moving 10 miles an hour to the right, and we have another car moving 20 miles per hour to the right, then the car moving 20 miles per hour according to the car moving 10 miles per hour, is moving 10 miles per hour
Sure.
to the right.
And that works for low speeds.
But
Galilean velocity transforms.
at what point does that no longer work?
So I was talking to one of your classmates yesterday about kind of general rules of thumb for how crazy relativistic something is. And gamma tends to be a good yardstick for this. And so, because remember, both distance and time are related by gamma to the quote unquote proper values, right? And so if we were to drop that U and call that a V, if I was to say even 1/10 of the speed of light, 18,600 miles per second, right? Not miles per hour, miles per second. A tenth of c, a tenth squared is 0.01, right? 1 minus 0.01 is 0.99. The square root of 0.99 is, I don't know, 0.995, something like that. 1 divided by that is basically 1, right? Where a change by, I think we decided yesterday it was 0.5 of 1%.
Yeah.
Could we measure that? Sure. I mean, is that an obvious change? No. if we doubled that to 20%, right? 0.2 times 0.2 is 0.04.
My question is about how we get that 0.1 though, that 0.1c. Like, because in this case, we're saying they're moving too fast for me to just say that the other one is moving 0.25c.
It's too fast for you to be able to say, well, Mark measured 0.1c for one and 0.2c for the other. And so I can just add or subtract those. Right?
Yeah, my question is.
But it's not so fast that Mark can't measure those. It's that you can't just blithely say, well, Mark measured that Dimitri was moving 0.2c and I'm moving 0.1c, so I could just add or subtract depending on the directions, right?
That doesn't really answer my question.
Uh-oh.
I'll let you move on with that.
Okay. I thought I was. I apologize if I misunderstood the question. So, okay, so so let me try one quick example problem before we spend a few minutes talking about general relativity. General relativity requires tensor mechanics, and so I'm not going to do that mathematically at all. But at the start of class, I was telling you that we're going to run our Compton scattering lab in the very, very near future. And so you get to use radioactive sources. Don't worry, I'm allowed to lose 2 students per semester. So it'll be fine. We're not going to use polonium, but if we did, do you guys know what radioactive decay is? We'll talk about it more once we've had some quantum under our belt.
Yes. Half something to the power something. I don't know that much.
Radioactive decay, if you look at our periodic table of elements, some nuclei aren't stable. You could probably suss this out on your own. Sure. I have faith in you. So if you were to think of the atomic nucleus, do you guys, someone probably already taught you this, meaning someone did my job for me, which I never complained about that. But what's in the atomic nucleus? What stuff lives in the nucleus?
Protons and neutrons.
Protons and neutrons, right? Charge of the protons, plus or minus?
Positive.
Positive. 1.6 times 10 minus 19 coulomb. Yay. Charge of the neutron?
Neutral.
0, right? So, do protons enjoy being near each other? That's an anthropomorphic statement.
No.
No. Size of the nucleus, you put 2 positive charges next to each other, they don't want to be near each other, right? You've heard the expression opposites attract, likes repel. I don't know if that's true for people. I don't understand people at all. But I do know that protons and electrons and charged particles in general do obey that type of relationship, right? So you could kind of think of a good rule of thumb for the size of a nucleus as 10 to the minus 15 meters. think of lucky hydrogen. Hydrogen doesn't have to share its nucleus with any other subatomic particles, right?
Yeah.
Occasionally it'll let a neutron spend some time there, but in general, the proton gets to be all by itself. Lucky proton. Then you get to periodic table, helium, right? Helium has 2 protons, 2 neutrons in its most common configuration. Sometimes you'll get 2 protons, 1 neutron. Yeah? You're never going to find 2 protons and no neutrons. Why not? Well, protons don't like being near each other, right? The neutron serves as kind of the mediator there. We'll talk about other forces. So you might imagine that once you start putting more than one positively charged thing into that tiny little nucleus, you have to start worrying about whether or not this is stable, right? Whether or not, like if you put me and my brothers into a room, my parents tried this. If you put us into a room and close the door, half-life, about 30 minutes before someone was going out a window. By choice or not, someone was,
Screaming.
if the door wasn't open, someone was going out the window. And you could choose to go out the window or not, but you were going out the window. You might imagine that there is something similar going. My brothers and I are also repulsive, right? I've been told this repeatedly. You might imagine that there's something similar to this going on with the repulsive effect between protons. By the time you get up to, say, uranium, then you have crammed so many protons into this nucleus that given enough time, someone's going out a window, right? That's what I want you to think of as kind of a good model for radioactive decay. So polonium is on this list. Polonium, if you've crammed enough protons and neutrons in there, given enough time, someone's going out the window. So if you wait long enough, that's not right. If you wait long enough, polonium is going to spit out a helium nucleus. So it'll get rid of 2 protons and 2 neutrons, leaving you with lead. Okay? Now, herein lies some of our problem. That if you very carefully account for mass, the mass of polonium-216 is 216.001905 U. The mass of lead-212 is 211.991888 U. The mass of helium-4 is 4.002603 U. If I add these together, what I get is 215.994491 U. Now, kind of care enough to try and...
Something missing.
That's the global point, right? It's not much that's missing, but something's missing.
Yeah.
It's mass that's missing, right?
Yeah. Where is that?
And so we run afoul of this idea that mass is another form of energy. really I should be careful here because what's actually happening is the binding energy between nucleons, protons and neutrons and such, is different in these different atomic nuclei. But if you looked at the total mass, you would say that there is a mass deficit. Now, if mass really is a different form of energy, then the way that this is going to happen is these particles are going to be carrying some significant kinetic energy. And so we can sort this out. This is the sort of thing I normally don't worry about when I'm teaching, because I am but a lowly experimentalist. But now I'm being recorded, and so I feel a little awkward doing this because I know the theorists would get mad at me for doing this. But we talk about a mass deficit, and here it winds up being about 1.23 times 10 to the minus 29 kilograms. Is that a lot of mass or a little mass?
Very little.
That is very, very little, right? Which, by the way, is also 0.007414 U. So we could look at how much energy this corresponds to. You might say, yeah, that's not much, right? Not much mass. But remember, we're multiplying this by c squared. And c is 3 times 10 to the 8 meters per second. So c squared is 9 times 10 to the 16 meters squared per second squared. And so E is about 1.11 times 10 to the minus 12 joules, which is 6.92 mega electron volts. Questions, comments, concerns about this?
What's the volts with
Mega electron volts, it's 10 to the 6 electron volts. An electron volt is 1.6 times 10 to the minus 19 joules.
Oh, okay.
So, all right, so this is kind of the root issue of nuclear fission power plants, nuclear fission weapons, right? The same would also hold for fusion. Fusion's harder, right? Fission's easy because for fission you just need some nucleus that has so many protons crammed into it that it's unstable, that it wants to break apart into smaller pieces. Because when that happens, you release a little bit of binding energy as missing mass. Fusion is harder because it's effectively taking, if you have hydrogen and you want to make helium, you have to take a pair of protons, hold them together, glue them together with some neutrons, right? That's not easy to do. So fission is the one that we have used first because it's easy, right? We don't have to do anything. We like it that way. Fusion is the harder case, but well, it's harder. Okay, so questions, comments, concerns about this? I'm going to spend a few minutes talking about GR. Maybe I'll spend a few minutes talking about this at the end of the semester too. Maybe I'll do that as kind of our going away lecture. So
It's not part of the exam though, is it?
I'm not going to test it on GR. So GR is just an amazing accomplishment, though. So I do want to at least speak about it in broad strokes. So this seems a little bit like an anachronism, but I know you look at me and you think that when I was a young person, we hadn't invented the wheel yet. But they actually had cars when I was young. So my parents didn't really believe in child labor law. And so I've been working since I was, small. I think I've told you guys, I've had pretty much every job under the sun. Babysitter, dog walker, I worked at the library, I assembled baby furniture at Sears, I did landscape gardening. Landscape gardening. I worked in a restaurant. I worked as a secretary. I've done lots of stuff. So my parents wanted me to put that money away for college, but what I really wanted was a car. And so when I turned 15, I bought a giant yellow Cadillac. This thing was huge.
VA Cadillac?
Yeah, I think it was a V8. So this thing was, it didn't have seat belts. This was before California had seatbelt laws. So I could fit all of my friends in this car. And you're thinking that's because I didn't have any friends. Even people who, didn't really like me, but just wanted to ride somewhere. So I got my driver's license as soon as I turned 16. I'd been driving for a year, but I got my driver's license when I turned 16. And by some miracle, it was almost Valentine's Day, I had a date. I don't know if she'd lost a bet to one of her friends or something, but I also wasn't gonna, I wasn't gonna ask. So I went to, the true story, I went to Broadway Plaza in Walnut Creek, See's Candy, and I bought 2 boxes of chocolates. Bought a little box of chocolates and a big box of chocolates.
Small for her, big for yourself.
Small for her, big for me. Even then, I knew no one was going to love me as much as I loved me. And
We all love you.
you're very kind, but not as much as I love me.
I don't.
So, I put them on my dashboard. I put the car in reverse. I backed away from the parking column, put the car in drive. I didn't mention this, but my car had a loose engine mount. And so every time I put this thing in gear, the whole car would kind of lurch, a giant engine. And so the car lurched for inertia. What did those 2 boxes of chocolates do?
Move forward.
No.
They stayed put. What did the car do?
Move.
The car
Forward.
moved forwards when I put it in gear. And so what happened? Well, the box of chocolates started to fall, right? They moved back towards me, right? Because I was moving with the seat in the car. But they stayed put. They started to fall. Most athletic moment of my life, I dove across the bench seat, giant car, and caught both boxes of chocolates before they hit the floorboard and had to be cleansed by fire. Unfortunately, I also stepped on the gas pedal,
Oh no.
and I put the car right back into the parking column I just backed away from, pushed the left front fender through the left front tire, and then spent the next year and a half in auto shop because my parents wouldn't pay to fix the car. But, well, it drove. It took me a while to get the fender out of the wheel, but I did. Loved that car. No seatbelts. What I want to talk about is those 2 boxes of chocolates. They both seemed to accelerate back towards me at the same rate. Where have I seen something like this before? If I were to drop these 2 things, they don't have the same mass, they fall at the same rate. Why?
Gravity?
Gravity.
Constant acceleration, gravity.
But note that these 2 boxes of chocolates also accelerated at the same rate, independent of mass,
Yes.
right?
Because of
Einstein sees something here that is going to be revolutionary, and I'm going to have to save that for another day. I'm out of time. As always, you guys are awesome. Have wonderful days. Thank you for stopping by. Don't be strangers. Enjoy your days, but not so much. We'll see you next time. I'll fix this for you guys later.
Okay, thank you.
Yes, sir.